Hi everyone. So in the last lecture today, I'm going to show you how the de Broglie wavelength idea allows you to find the formula for the energy levels of a hydrogen atom. So just to remind you, the idea of the de Broglie wavelength is that you can associate a wavelength to any sort of particle by dividing the Planck constant by the momentum of that particle. Okay, and in particular, for an electron inside hydrogen, we assume that the electron is going around in a circular orbit, as shown in the picture here. And for the quantization condition, we assume that the total distance traveled by the electron over one orbit should be an integer multiple of its de Broglie wavelength. So this was shown in the PPT last time. Gives you a set of pictures like this. Okay, so for example here, in this first picture, the total distance traveled by the electron around the atom is 3 wavelengths, and then this one is 4 wavelengths, 5 wavelengths, 6 wavelengths, and so on. Okay, so what we want to do in this lecture then is to use this idea to derive a formula for the energy that these electrons are allowed to have. And we'll see that this gives the correct formula for the quantization of energy. Okay, so first of all, we need to do a bit of classical mechanics. Note that in this case, we'll find that the velocity of the electron is much, much less than the speed of light. Okay, and that means that Newtonian mechanics is okay. So we don't need to worry about relativistic formulas for momentum and so on. Okay, so in particular, the momentum of a electron is just going to be its mass times its velocity v. So also from Newtonian mechanics, we know a formula for the force on this electron required for it to go around in a circle at constant speed. And that is given by the formula here. Okay, so the force on the electron to make it move in a circular orbit at constant speed is simply equal to the mass of the electron times its velocity squared, or its speed squared, sorry, divided by the radius of the circle r. Okay, so I'm assuming you've seen this formula before in a mechanics class, so I'm not going to prove it. If you haven't seen this formula before, then you can ask on the WSQ sheets this week, and I will show you the derivation of this formula. Okay, but in this video, we're just going to assume that this is the correct formula for the force required for the electron to move around in a circle. Okay, so that sets up the problem, and now we can just proceed with the calculation. So the force on the electron here is electrostatic force, right? The proton is positively charged, the electron is negatively charged. So it's an electrical force, and we know the formula for the force. It's just constant, so 1 over 4 pi epsilon 0 times the product of the two charges. Well, in this case, both proton and electron have charges of equal magnitude e, divided by the distance between the two particles squared. Okay, so this is the law for electrostatic force here. Okay, and therefore you equate this force equal to the force required to make the electron go around in a circle. We see that 1 over 4 pi epsilon 0 v squared over r squared must be equal to m v squared over r, and I want to be able to write this in terms of the momentum, so we can use the de Broglie wavelength. But if the momentum is m times v, then I can write mv squared as p squared over m. So we get this. Okay, and notice that this therefore gives you a relationship between the radius of the orbit of the electron here and the momentum the electron will have as it moves around the orbit. So namely, we get that P should be equal to m over 4 pi epsilon 0 r square root. E squared. Let me see. There we go. Okay, so that gives you a formula for the momentum in terms of the radius of the orbit. I'll call this formula A because we'll use it a lot in a minute. Okay, so next, we can now use the de Broglie formula to find the wavelength. Okay, so that's just h over p. So this is h times me squared over 4 pi epsilon 0 r to the minus a half. And finally, we can use the quantization condition. The wavelength must be equal to the total distance around the circle divided by some integer n. Okay, and if we put that in, we get that 2 pi r over n is equal to h times me squared over 4 pi epsilon 0 r minus a half. Okay, so in this equation we can see that the only variables we have are r and n. Okay, everything else is a constant. So this means there must be a relationship between the radius of the orbit r and this integer n. Okay, and therefore that means that the radius of the orbit is quantized. It can only take on certain values given by this integer n. Okay, so we can easily work out what the formula for r is. If we square this equation, then we get 4 pi squared r squared over n squared is h squared times 4 pi epsilon 0 r over me squared. Okay, and we can cancel one factor of r, we can cancel one factor of pi, we can cancel the 4's. So putting all that together, we get the r, and I'll label it by n to show that it depends upon this integer n. Rn is equal to h squared times epsilon 0 divided by pi times m times e squared times n squared. So that's the formula for the quantization of the radius of the orbit. But what we're interested in is the energy of the orbit, right? So next we have to talk about energy. So the energy of the electron has two terms. It has a kinetic energy term, and it has a potential energy term. And the potential energy, again from the electrostatic force law, is minus 1 over 4 pi epsilon 0 times the product of the charges divided by the distance between them. Okay, so this we can write, again use the same idea to rewrite velocity in terms of momentum. So this is p squared over 2m minus 1 over 4 pi epsilon 0 e squared over r. Okay, but now if we go up and we look at the formula for momentum here, A, we see that if we square this, we get a term which looks very much like the potential energy term down there. Okay, so I'll put it on the same line here so I can see this formula. So p squared over 2m is just going to be equal to e squared over 8 pi epsilon 0 r minus, and then the potential energy term is e squared over 4 pi epsilon 0 r. Okay, so in this case here we use the equation A for the momentum. Okay, so these two terms are the same, but the first one is half as big as the second one. So we put this all together and we get that E is equal to minus e squared over 8 pi epsilon 0 r. Okay, and then because r is quantized, E is also quantized in this formula. So this tells you that you do have quantization of energy. Okay, which is what we wanted. And finally, to work out the formula for this, we just have to put the formula C for the quantization of radius into this formula for energy here. So lastly, formula C implies that En is minus E squared over 8 pi epsilon 0 times 1 over Rn. So 1 over Rn is pi m E squared over h squared epsilon 0 1 over n squared. Okay, and pi's cancel, and the other terms we can combine together. So this gives you the formula En is equal to minus me to the power 4 over 8 h squared epsilon 0 squared. These are all just constants, and multiplied by 1 over n squared. Okay, so this is the final result. And notice that, as predicted by Rydberg, the energy is a constant times 1 over n squared, where n is an integer. Okay, and if you evaluate this constant here, all of these are physical constants which are known, then this turns out to be minus 13.6 electron volts. And we actually used this result when we were talking about the change in mass of the hydrogen atom as a result of bringing this proton and electron together. Because they are losing electric potential energy as they get closer together, that means that the mass of the hydrogen atom is less than the mass of the proton plus the mass of the electron. And the difference is precisely this, the energy lost by the electron going into the ground state. Okay, so that's the end of this video, and this does show that you can get the correct formula for the quantization of hydrogen energy levels by using the two ideas of de Broglie. Firstly, that you can associate a wavelength with the particle depending upon its momentum, and secondly, that in the case of an electron going around a nucleus here, the total distance traveled by the electron in its orbit should be an integer multiple of this wavelength. Okay, so that's the last video for this week.